And we're back from staff meeting. So, continuing on with the physics. So, where we left off with our previous video was talking about this device right here. So, as you can see, once I select a pen tool here, that this guy is called a commutator, also called a split ring commutator. And the cool thing about a commutator is that what it does is it switches the direction of the current. So, as you can see with this electromagnet in the middle here, is that as it's going to be repelling this way, the force it's experiencing is this way. Well, this here would have a south pole in its electromagneticness. This guy would have a north pole, so they're going to repel each other. Well, as this part of the wire loops up and over here, well, guess what? There's going to be an attraction there. So what the split ring commutator does is it changes the direction of those little electrons. So therefore, it's going to flip the direction of your magnet. So that way we are going to be continually having repulsion there. So which just means we're continually going to be having that force, which is going to be spinning that wire. So which is pretty cool. All right, so enough with that diagram there. Let's look at a couple of examples. So, couple theory, couple calculations. This is a shorter topic, so we won't be too long. So, if our conducting wire, let's get the pen tool here. If your conducting wire is deflected towards the back of the U-shaped magnet, determine the polarity of the magnet. All right, so what we have here in our diagram is we have our negative end of the battery. Remember that your negative end of the batteries is the source of electrons. Those of you who took Chem 30, the negative end of the battery is called anode. Okay. So it is going to be your source of electrons. So that means our electrons are going to be flowing through the wire like that. So, and the force is going to be towards the back of the magnet. So this, oh, come on. There you go. Let's change colors so you guys can actually read that. There we go. So this here arrow is going to be the force that we are experiencing. So left-hand rule, ladies and gentlemen. Okay, third left-hand rule. So let's write that down. Third left-hand rule. You're going to take your left hand. You're going to point your thumb in the direction of the electrons, which is going that way. Okay. Now the force is going to be going towards the back of the magnet. There we go. So if electrons are going this way, and the force is going that way, what's our hands pointing? Fingers pointing up. So that means we are going to be having our pole of the magnet pointing this way. So in this diagram, that means it's going to be going like that. Remember, our arrows are going to then point from north to south. We've determined the polarity of our magnet. Yay! Sounds good? Any questions? I can't answer that. Email me if you have any questions, but not to my EDU account, to my regular GPCSD account, please, and thank you. Okay. So I'm going to scroll down to our next question here. We're going to get to said calculations. So I'm going to go back to red. There we go. Oh, come on. All right. So a 1.20 meter long copper wire has a mass of 9.02 grams, is carrying a current of 5.10 amps perpendicular to a uniform magnetic field. Okay. So what we have learned by reading all of this at once is we've learned that entire wire length is going to be inside that magnetic field. That might not always be the case, so please keep in mind that it may not be the case, guys. So watch for that. So I'm going to write my length perpendicular is going to be 0.120 meters long. And now the mass. Ladies and gentlemen, can we ever use grams as mass in physics? No, use kilograms. So we're going to take this guy and we're going to convert this into kilograms. So it's going to be 9.02 times 10 to the power of negative 3 kilograms. And then we have our current, which is our I. Now notice how I wrote my L as a handwriting L and then my I as a capital I. It's so much easier to tell the difference with these guys when you distinguish them somehow. So 5.10 amps. That's a lot of amps. That's like 500 times plus the amount needed to stop your heart. 5,000 times needed to stop your heart. Something like that. It's a lot. It's a lot of amps. Okay. And this is placed in a strong magnetic field and the wire is found to levitate. Now, ladies and gentlemen, if we are going to be having a levitating wire, that means we're floating. Okay? If we're floating, that means we are going to have an F net on the vertical is going to be 0 newtons. So when we're going to be looking at our wire, I don't know, let's make our wire going into the plane of the page. Why not? So that would mean our force magnetic field and our FG are going to equal each other. Okay? So let's write ourselves out a F-net equation. You guys love F-net equations. I love F-net equations. So our F-net is going to equal our Fm plus our negative Fg. Now, because our F-net is going to be 0 newtons, that means my Fg is going to equal my Fm. Okay? Now, we scroll down a bit. Okay. Now, as we know, Fg is always equal to mg. And now my lovely brand new shiny equation is IL perpendicular, and we're going to multiply that by our B. Okay. Now I'm trying to find the strength of my field here, so I'm going to divide out my I and my, that's supposed to be an L perpendicular. So divide out my I and my L perpendicular. Okay, those guys cancel. And my value of B is mg over IL. There we go. Now it looks nice. There we go. L perpendicular. So I'm going to now put my beautiful numbers into my equation to get my value of B. And my mass, 9.02 times 10 to the power of negative 3. Multiply that by 9.81. Okay. And now I'm going to divide by my current. Multiplied by the length of the wire. What was that again? We're going to have that 0.120 meters. Okay. So my value of B, which will be perpendicular to the wire, is going to be, get it? Going to be, yeah. Okay. Laugh at my jokes. I'm in here by room by myself talking to my computer. I'm the only one laughing at my jokes. You guys better be laughing at my jokes. Please. Okay. 2, 1, 4, 4, 5, 8, ... 4 significant digits. Ladies and gentlemen, we want 3. So 0.145. I am going to scroll up so I don't have to write on my face. Tesla. Okay, now when we look at the question, you're going to see that it says magnitude of the magnetic field. It's not asking for direction. You haven't been given enough info for direction, so that's a very good thing. They're only asking for magnitude. box your answer so that way I know what you want me to mark for your final answer. All right. So moving on to our next two questions before we call it a day. We're now going to be looking at a novel scenario with a pen instead of a mouse cursor. Is we have a wire with a length here. It's got a current of 2.78 amps. That's still a lot of amps running through it. And it's now 56 degrees to the magnetic field with a strength of 5 Tesla. What is the magnitude of the force experienced by the wire? Now, we have a problem. We're at an angle, guys. And remember, our equation is that of perpendicular. So we need to go and do some trig, your favorite trig, woo! And we are going to be determining the length of the wire that's actually perpendicular to the field. So let's draw this. And let's do blue for our magnetic field. That's kind of what we've been using so far. So if my field is going like this, here's my magnetic field going like this, and let's jump back over to red, and my wire is going to be like that. This is really not turning out very well. It's really hard to draw here, guys. Okay, that's supposed to be a straight wire. Yeah, bear with me. Okay, and it's at 56 degrees. Okay, so 50 degrees, 6 degrees to the magnetic field. I'm just going to make, because this is perpendicular, this is the horizontal. Okay. So there's my 56 degrees. Well, now I'm going to break this into X and Y components, and I'm going to think about which of these is going to be, let's go pink. Which of these is going to be the length of the wire that's actually perpendicular to the field? So there's my Y, and there's my X. So let's think about this. Oh, the Y, this part here is parallel to the field. This guy here is perpendicular to the field. So that is what I am going to use. Now this guy here, my 1.44 meters, that is going to be the hypotenuse of my triangle. Let's draw this out as actually a triangle that we can kind of even tell is a triangle. This is supposed to be a right triangle, guys. Please forgive me. Yeah, 56 degrees. And then we've got your 1.44 meters there. Well, I want to find the value that is going to be this. I'm just going to call it Y. It's on the Y-axis according to my view. So I need to find the value of Y there. Well, I'm going to use sine because I've got the opposite to this, to my angle, and I have my hypotenuse. So I'm going to go with my 1.44 sine of 56, and that's going to equal the value of my Y. Now, ladies and gentlemen, make sure your calculator is in degrees and not radians, since you have definitely been doing your math homework and you would likely have been radians. Switch to degrees, because if you don't put your calculator into degrees, you're going to have a rad time. Please be laughing at my jokes, guys, even if I've told this one before. Announcement, hold a sec.
Chester, can you please come to the office?
Okay, Chester's a popular man. Chester's cool. Okay, so once you put this into your calculator, our Y value is going to be, once I actually look up what I calculated it as, is going to be 1.193 ... meters. Okay, so that is going to become my length perpendicular. You are going to use all of these values in your calculator. Never round midway, always round at the end, because if you happen to have a diploma, that's at the end of the year. That's how they're going to get their diploma numbers. Rounding at the end only. University, they'll do that too. So round at the end. And now we need to calculate the magnitude of the force in that wire is going to experience. So Oops, hey, I can click with that thing. So, oh, come on. There we go. So let's calculate our F magnetic is going to equal our I length perpendicular times B. Well, we have our length perpendicular, which is here, and we have our current here, and we are now going to have our B of 5 Tesla. So my FM, I'm going to take my current of 2.78, that's a lot of amps, and then I'm going to multiply that by my full number, my 1.193. I have an extra 9 in there somehow. Let's make this purdy. Well, if you can call my writing purdy. I don't think it's ever had that description applied to it before. There we go. All digits, remember, all digits. And then we're going to multiply that by our B, which is 5 Tesla. And you're going to get a magnetic force equal to your 16.6 newtons. And the question says magnitude, so therefore you don't have to give me direction. I got my 3 sig digs. Box your answer. Tell me what you want me to mark as your final answer. And we're good. Okay. I keep wanting to say any questions, ladies and gentlemen. I'm so used to talking to you guys, not to my computer. Okay. Okay. So once again, email me if you have questions. Okay. Hey, cool. I can click with this thing. It's kind of cool. Stylus majig. Okay. So let's look at our setup here. So we have a magnetic field strength with a horseshoe magnet here. And we have our magnetic field strength there is going to be 0.335 Tesla. And what magnetic force is acting on the conducting wire when we have a current of 2.65 amps? So let's do some thinking here, ladies and gentlemen. Now, I haven't given you all the information we need for this question. We're going to do some labeling before we even get to this question. So first thing, let's determine the direction our electrons are going. You see this short end? That's your anode. So for those of you who took Chem 30, your anode's the source of the electrons. And so that means they're going to be going this way, like that. Okay? And then like that through the wire. Now let's think about this length of the wire. Let's pretend, what did I decide on earlier? 15 centimeters. From here to here is going to be 15 centimeters. However, I'm going to switch colors so it's easier to see. We'll go back to blue. The length of the wire that's inside the magnet from here to here is going to be 2.5 centimeters. We are not to scale. So when I'm going to be picking my values for the force that this thing is going to be experiencing, what do I pick? 15 or 2.5? Think and decide. If you said 15, you're wrong. If you said 2.5, you're right. 2.5 is the answer, ladies and gentlemen. Why is it the answer? Because that's the length of the wire that's actually going to be experiencing that magnetic field. The remainder of it isn't. So it's not going to be contributing to that force. So when we come to our L perpendicular, we are going to use that 2.5 centimeters, not 15. Okay, so I would even make a note here. Don't use 15 centimeters because not all is in the field. So there's your note for your notes. All right. So scroll down a little bit so we can have some space and you guys can see for your calculation. So we are trying to calculate the magnetic force. Okay. So our force is going to be your I L perpendicular times B, should be force M, force magnetic. So our current is 2.65 amps. Our B is 0.335. I'm going to make a mistake here. I'm going to ask you what it was. I'm then going to put 2.5 here. What's my mistake? You're right. I forgot to convert my units. So for those of you who are going to be handing in your assignments to me, you have to convert your units or you cost yourself half a point. Okay? Okay, 0.25 meters. Okay, so you're gonna get your magnetic field of, yeah, I did right. Oh, I wrote these in the wrong spot backwards. Whatever. It's multiplication, it'll be the same. So our force magnetic is going to be our 0.02219. That's super messy. And dot. Scroll down. Okay. Pen. So we're going to need to add correct sig digs direction unit. I said force. I didn't say magnitude of force. So we're going to need direction here. So looking at sig digs, I'm going to want 3 sig digs. Now, the leading zeros aren't significant. So 0.0, these are going to be significant here. So 2 newtons. Now, I'm going to need to go back up to my diagram here so that way we can determine our direction. You're going to determine your direction with your third left-hand rule. We're dealing with electrons flowing, so take your left hand. Hello. And we are going to point our thumb in the direction of the current, which is going that way in our diagram. And then we are going to have our fingers pointing in the direction of the field, which is kind of that way. And then we're going to be looking at the force. Well, look at that. The force is going down. So that means we are going, no, I screwed up. I've got my field arrows going in the wrong direction. Okay, it's almost the end of the day, guys. I'm getting kind of tired. So there we go. There we go. So if we have going like that, that looks like an up to me. So we are going to have our force, which is going to be going kind of up like that. Okay. So now we're going to come down here and I'm going to jump back to red. Up. Okay. So, ladies and gentlemen, come on, there you go. Box your answer. Input up. All right, so ladies and gentlemen, you guys can see you got some practice problems to do here. And give those a shot. Do some practice problems. Chip away on that one assignment you have for this chapter. And we go from there. So after this, ladies and gentlemen, we've got one more topic for the last piece of this unit. And that is going to be electromagnetic induction and Lenz's law. I always find it weird that Lenz's law doesn't relate to optics. I'm going to find that weird. Okay, so ladies and gentlemen, we will see you later. Have a good rest of your day. No fires, injuries, or explosions. Turn off. See ya.